Hi, colleagues and professor. Today we are going to talk about optimization-based demand response. So, just before moving on to this, I would like to share a video regarding the rise in the price of electricity because this has something to do with the optimization-based demand. Though we have a technical thing to discuss, but just wanted to share this with you.
Today's a tough day. It's a tough day for Ontario and for Canada, just as much as it's a tough day for the United States. Because, well, there's no question President Trump's tariffs on Canada will hurt us. They will also hurt Americans.
Thank you very much. The tariffs, as you know, will start a week earlier than the reciprocal, which is going to be on a couple of weeks earlier. Reciprocal tariffs start on April 2nd. And I wanted to make it April 1st, but I didn't want to go April.
So just moving it a little bit faster. So let's begin with our recent today's discussion, which is regarding the optimization-based demand response. So in this brief presentation, I will be presenting you the basic concept, though most of us we know about it. Just a little bit regarding the optimization based demand response, and then we will move on to next. Like this is like a kind of introduction or proposal uh, that I would like to discuss here. So in this project, it's a comprehensive analysis of cost and peak reduction strategies, and we will talk about especially case study for Ontario's electricity grid that faces peak demand challenges. So, which is very important topic we should discuss. Ontario's electricity grid faces challenges related to peak demand periods and high electricity costs. Demand response DR and load side management offer solutions by optimizing energy consumption based on pricing signals, grid constraints, and user flexibility. Industrial applications stand to benefit significantly by reducing peak loads, enhancing energy efficiency, and leveraging uh, financial incentives. So the integration of optimization-based DR strategies allow for improved energy management, reduced operational costs, and better sustainability. So we will talk about these aspects one by one, and we will talk about the objective. Our objective is to develop an optimization based model for DR to minimize electricity costs, reduce peak demand, maintain user control, and adhere to grid limits. So this is our task. So how we will do is like we will be working on like minimizing electricity costs through efficient scheduling, reducing peak demand to lower stress on the power grid, by maintaining user control constraints, by ensuring the essential loads remain uninterrupted. So adhering to grid limitations and taking advantage of financial incentives for peak shaving. So we will be working on the methodology that we can talk about our approach as well. What would be and what I suggest is one is that demand response model will be formulated as a mixed integer linear programming, MILP, or non-linear programming, NLP problem to optimize load scheduling while considering real world constraints. So in MILP, it's used when decision variables involve binary on and off states, for example, turning devices on and off at certain times. Another is NLP, is used for more complex nonlinear relationships, for example, thermal comfort modeling in HVAC systems. So for the model formulation, we have decision variables and objective functions. We can talk about those methodologies as well. In that case, if we talk about the decision variables, power consumption scheduling for controllable loads determining when and how much energy is consumed. And the objective function is like minimize the total electricity cost and peak demand penalties by shifting loads to non-peak hours. So the constraints are load flexibility, user preferences, grid limits, financial incentives. So set for the load flexibility, certain loads such as HVAC and EV charging can be shifted within allowable time windows without impacting operations. And one constraint is user preferences, comfort constraints for heating, cooling, and essential equipment to ensure user satisfaction. And grid limits constraint is like capacity restrictions from the utility provider, ensuring grid stability. And for the financial incentives, utilizing time of use pricing, demand charges, and incentive program for demand side participation. So, in this is just the beginning of the a discussion. So we can talk more about industrial applications, particularly in Ontario. Industrial demand response. If we talk about industries, can shift non critical loads, for example, refrigeration, HVAC, and batch processes to off-peak hours to reduce electricity bills and avoid demand charges. Optimization can improve load scheduling based on real-time pricing, allowing for cost saving and better operational efficiency. And on the commercial sector implementation, commercial buildings such as malls and offices, complexes can benefit from demand response through intelligent HVAC and light controls. Automated DR strategies can help reduce peak demand while maintaining comfort levels for occupants. For the residential demand management, um, smart homes equipped with IoT-enabled devices can participate in DR programs by optimizing appliances used, for example, electric water heaters, EV charging, and smart thermostats. Based on TOU pricing, machine learning algorithms can further enhance demand forecasting and scheduling. So the implementation framework we can talk about that particular area as well. That's how we're going to deal with the implementation framework. So in that case, data collection is important. Real-time electricity pricing from independent electricity system operators, like ISO, historical load consumption data from residential, commercial, and industrial users, and demand-side management incentives and policies in Ontario to ensure compliance and maximize financial benefits. So this is what we can do. And regarding the challenges we will be facing during the project or during the studies, and depending upon the scope of the project, we can talk about those challenges. One is the consumer participation, data accuracy, complexity. In solutions, we have challenges in incentives, smart metering, AI-based forecasting. Like these are the solutions, but we have to face a few challenges. I couldn't mention all of them. There are like a few of them here. Then I would like to share with you a case study of the Toronto Hydro Peak Saver Plus. This is a program that talks about, if I can, let me grab the PowerPoint presentation if I could, because in the next session, hopefully I'll be talking more about the case study where the Toronto Hydro, that is Peak Saver Plus program, it manages peak demands using smart thermostats and automated DR technologies, achieving a 15 to 20% peak reduction. So I have a separate PDF file. We can talk about it. So the case study outcomes are that they reduce electricity consumption during peaks. Another is increased customer engagement, and that lessens tech integration participation incentives. So these were some of the goals. So in this today, it's like a brief summary of the project I'm going to do. So we will conclude and come up with solutions, and we'll see what future work is supposed to be done. Um, for me, what I collected, like what is required for and what should be the expected outcomes. Cost saving should be one of the expected outcomes, low grade congestion, and increased participation, and actionable insights as well. So, uh, if we talk about the proposed solutions, one is the user incentives, another is smart metering and IoT integration, and the efficient algorithms. So we have to work more on the algorithms and collaboration with the utilities. When we talk about user incentives, financial rewards, and real-time notifications to encourage participation. Another is smart metering and IoT integration, enhancing data collection through smart meters and connected devices. Then the efficient algorithm is the part where I can work leveraging machine learning and parallel computing for faster optimization. And for the collaboration with utilities, working with IESO and local distribution companies to ensure regulatory alignment. So this project offers a robust framework for industrial, commercial, and residential demand response in Ontario by leveraging advanced optimization techniques and real-time pricing mechanism. It ensures cost-effective and efficient load management. Implementing such solutions will benefit consumers, utilities, and grid operations by reducing costs, improving grid stability, and enhancing energy efficiency. So the future work, when we talk, I think it's one is the renewable energy integration, incorporating solar and wind generation into DR strategies, then the user-friendly dashboard development, designing an intuitive platform for user to monitor and manage their energy consumption. And the most more important where we can help is the machine learning for predictive demand response, utilizing AI to predict energy demand and automate scheduling for greater efficiency. This is where we can work. At the end, just showing you a video, a small video related to it's like some kind of simulation based. It's at the YouTube, so I would like to share with you. It's very well done here. So let's have a look at this. Yeah.
Management and Decisional System Demand Side Management Concept. In this video, we'll talk about demand side management concept, objectives, and approaches. At the end of this module, you will be able to understand what is demand side management, why it is important, what are the benefits of demand side management, what are the objectives of demand side management, what are the programs of demand side management. Every day, customers from different areas such as industrial, commercial, and residential need electrical energy for production, business, and households. Despite increased efficiency of electric devices, electricity consumption is steadily rising up. Demand of electrical energy also varies over a day. It goes up and down and reaches its peak value. For example, in an office area, usually low consumption is observed from 6 p.m. to 6 a.m. However, during working hours, the demand on energy reaches its peak. Variation in demand can be observed not only over the days of the week, such as working days and weekends, but also according to seasons, weather conditions, geographic location, people's lifestyle, and special occasions such as public holidays and festivals. New technologies like electrical cars can also change the demand pattern. In order to fulfill the demand of electrical energy, power plants have to increase energy generation, which in turn leads to an increase of load on power stations, an increase on the price of electrical energy, and a negative impact on the environment. In order to solve these problems and to provide reliable and affordable energy to consumers, demand-side management concept has been introduced.
So this would be our task. So what we will be doing, this is just the beginning of the project. So I will come up with solution, strategies, approach, algorithms, and possibilities how um, we can get the targeted goals in this project that we can talk and for any questions because. It is just the beginning. I'm not having a solution or algorithms designed yet because we were very busy in doing so many other things. So hopefully in coming week or so and in next presentation, I will come up with more solutions. And I would love to have suggestions from colleagues, friends, and from the professor related to my work. Thanks for your time.